Quantum field theory describes how particles interact with each other, and this has become the basis for many modern scientific applications like particle physics and cosmology. But what are the mathematical origins of quantum field theory in physics? To understand the mathematical origins of quantum field theory, we need to go back to the early 20th century when quantum mechanics was first introduced. At that time, physicists were trying to explain the behavior of particles at the atomic scale, and they realized that classical physics wasn't sufficient to describe these phenomena. One of the key ideas in quantum mechanics is that particles can exist in multiple states simultaneously, a concept known as superposition. Another key idea is that we can't know the precise properties of a particle until we measure it, and even then, the act of measurement can change the particle's properties, known as the observer effect. These ideas were revolutionary, but they also raised new questions about the fundamental structure of the universe. This is where quantum field theory comes in. At its core, quantum field theory describes how particles interact with a field, which is a mathematical construct that exists throughout space and time. This field is made up of quantized particles called bosons, and they mediate the interactions between other particles. To understand this better, imagine a sea of particles, each with their own field, that interact when they come into contact with each other. This gives rise to waves that travel through the fields, and these waves are what we observe as particles. The mathematical framework behind quantum field theory was first developed by Paul Dirac, a Nobel Prize-winning physicist, in the 1920s. He showed that particles could be described as fluctuations in a field, and he developed a mathematical equation, known as the Dirac equation, that describes the behavior of particles in this field. However, Dirac's equation only worked for particles that have no mass, like photons, and it wasn't until the 1950s and 1960s that physicists were able to extend this framework to include particles with mass. One of the key discoveries during this time was the Higgs boson, which is a particle that gives mass to other particles. Theoretical physicists had predicted the existence of this particle, and it was finally discovered in 2012 by the Large Hadron Collider at CERN. Today, quantum field theory is the foundation of many areas of modern physics, including particle physics, cosmology, and condensed matter physics. It's also used in many practical applications, including electronics, nanotechnology, and quantum computing. In summary, the mathematical origins of quantum field theory in physics can be traced back to the early 20th century, when physicists were trying to explain the behavior of particles at the atomic scale. The development of quantum mechanics led to the realization that particles could be described as fluctuations in a field, and this gave rise to the mathematical framework of quantum field theory. Today, quantum field theory is a fundamental part of many areas of modern physics and has practical applications in many fields.